So who knows if this works, but we'll give it a shot. So one of the reactions that you're going to get hit with is the Sandmeyer reaction in this particular sequence. So if we just quick review that it's there, ta-da, be aware of it, and then we'll jump back to the homework. So starting off, do what I want. What do we have to start with? Question number 5. I think it's a grouped question. Oops, sorry, I'll put it up on the other screen. And as a grouped question, you may see other variations of this, but it's the same general concept, some kind of synthesis. So we're starting out with benzene structure. What's that first sequence of reagents do? This is our NO2 plus, which means as a result of that first reaction, since it doesn't really matter where we go through and put that hydrogen, we can put it wherever we want or do our substitution. We can get that NO2 on there. What's the next reagent do? Does a full reduction. Takes us the NH2. Now, potentially the tricky one, what's that next one do? I thought you said you had questions about this, so I'm a little confused. Oh, okay. So the replacing the diazonium with the OH group has to do with the next step. So that's what that next step is. Yellow is going to be an awful color for this. Let's try purple. So when we're looking at Ki, the whole point of that is now replacing the diazonium with iodine.
So if we had something, some other kind of ionic bond like NaOH, then it would replace it.
I believe so. That's where that slide came into play, and I can backtrack to that slide. That summarizes your common reagents. So effectively, if you see that diazonium, you're going to do in the next step, you're going to do a substitution for the most part. What's the last step? So this gets a Cl plus, puts a Cl on the ring. Are all places on the ring identical? So we've got to make sure we place that Cl appropriately. Okay, to decide where to place it, we have to recognize we have ortho, meta, and para positions. And we have to know what atom X, iodine, is going to do in this case. Does atom X have more electrons or less electrons than a hydrogen? It has more, which means we'll come into that language a little bit. So I has more electrons. What the heck just happened there? Oh, it just took away my annotation abilities. Fucking lovely. Yeah, you're just a complete asswipe now. And it's probably recorded, even better. So I has more electrons than iodine, and I can't annotate for whatever reason right now. So in that scenario, it has more electrons than hydrogen. You're not wrong to make the suggestion whether it's activating or deactivating. However, is that relevant? No, I'm not being asked about speed. What I care about is where the substitution is going to happen. Okay, that's my only focus. So activating and deactivating is kind of a secondary aspect unless you're using activating and deactivating as a memory trigger to call where it substitutes. Does that make sense? Okay, so it sounds like, at least in your head, what you're doing is associating the activating term to mean ortho and para. I want to do a tweak on that. You shouldn't memorize it as activating ortho para, because when you memorize it as activating ortho para, where are you going to do your first substitution? Ortho, except it's not that it could be, it is para. So, and you'll probably notice in the recordings that I reflex into activate ortho para, and it may actually be an English language thing that we're used to alphabet, and so we want to call it ortho para. I would highly encourage you to memorize activating as para ortho, because para is going to predominate over the ortho. Why? Sterics. The para is less sterically hindered than the ortho. We typically see the para substitution happen first, then the ortho. Okay, so for this particular scenario, which again, I may or may not be actually able to draw here. Got screens inside screens. Cool. Nope, nope, not going to happen. Maybe. How did that go to a 5-member? Put the chlorine at the para position. So you got the iodine and the chlorine direct opposites of each other, and that should be your answer. Does that make sense? So the decision on whether it reacts more than once in a multiple choice scenario, it's not asked, number one. And I would say number two, you're potentially going to see it show up twice. Yeah. With this one, should it happen more than once? So this is going to double back to our iodine and our chlorine. I'm going to try and draw a hexagon. Why? Should it react more than once? What do you guys think? Why? Inductive effect? What do you mean? Because if you're saying inductive effect, you're saying that that group is acting as what? An activator or a deactivator? Deactivator, because I said activator. So you're calling her a liar? Create some fights. Okay, and this is a weird one. Our halogens straddle that line, which is why I wanted to come back to your initial assessment. The halogens are not activators, they're deactivators. Which gets really weird because if they're deactivators, where should they direct? Meta, and yet it's directing para and ortho. Okay, your halogens hit the line. So activators are para ortho, deactivators are meta directors. The halogens straddle that line perfectly. They take a little bit of both. So they will be deactivators, but they will run substitutions at your para and ortho positions. The why they do substitutions at the para ortho, they have lone pairs. The lone pairs can donate through hyperconjugation. Activating is a strong word, but placing electron density at the para and ortho position. But because they're electronegative, they don't want to do that donation of electrons, which is why they're deactivating. Okay, kind of makes sense? Well, equally is a bit of a stretch as far as you're concerned, yes. Make sense? Yep. So in this particular case, because you talked about running multiple times. I would argue anytime you're looking at these, they're running single times. It's very rare for an overall reaction to expect you to predict multiple times. Okay. Um, so if we're going to run it once, it should run to the chloro or run to the para position. And then at that point, we've added a second deactivator to the ring, which is going to slow the reaction even further. Make sense? Okay. So I think I can cheat slowly. Maybe, maybe not. So you can see how much of a liar I am. Yep, there it is. Cool. And there we go, opposite sides. One thing to watch out for, how is this different than what I drew? Doesn't it look like the chloro's at the meta position? Isn't the chloro at meta and the iodine at the ortho? You got to be real careful that you aren't locking ortho meta para to the sides and to the angle and straight down. That's not where your ortho meta and para are. They're all relative to a particular group. So as soon as we've turned that structure, the chlorine is still para. It's para to the iodine. Kind of makes sense? Which then takes us to our next reaction. What happens in this case? Let's see if the tech's going to work with me this time. Why are you not drawing? What is this pen? No idea why it's not drawing. Okay, so if we're taking a look at that one, that first reagent does what? That nitro, again, doesn't matter where we place it. Next reagent. Okay, the Cl now needs to do a substitution, but we already have that nitro on there, which means we have to dictate where that chlorine is going to go. Because we have that nitro, we're going to direct to the meta position. That drops our chlorine there. Next reagent does what? Gives us the amine. Next reagent. Our diazonium. And then the last reagent, make sure we put on the iodine. Black was a horrible color for that. Let's just make the bond really long. Kind of makes sense?
So using the same set of reagents, we have to do any different work.
Ah, and this is exactly the most common way that ACS asks synthesis reactions. Right? They'll pick EAS reactions because the EAS allows you to do substitutions at different spots on that ring, and you can change the order in which those reactions happen or the location of where those are based off of swapping the order around. Okay? So you have to pay very careful attention to the order in which your chemical reactions are running. I would argue this is a perfect case where you draw it out. You draw out each of those cases. Okay. This is also where it's most relevant to have those reagents memorized, which is what I said for the EAS anyway. Okay. Memorize what those reagents do. It's now just a question of shifting those pieces around to get to your final answer. Make sense? And again, because we have the ability, we can scroll and we got it. Does that work? Okay. I'm going to talk through just a little bit, just talking. So we're just going to stare at that screen for a little bit. I just took the ACS exam again just to get a feel for where I'm getting things wrong, if I'm getting things wrong. I got 2 questions wrong. So there are 2, I would argue, challenging questions. And as I was answering it, I was like, I should probably go with my gut because my gut's telling me this, but I'm going to put this anyway. And sure enough, I got them wrong. And my gut was right. So within that, I'll blanket statement right away that two questions get curved immediately. Okay. So whatever your score is, I'll add two to that and then deal with curves and everything after the fact. Kind of makes sense? There are some questions that I disagree with, um, kind of for philosophical reasons. I do think every question is well within your realm. There have been other versions of the exam that have straight up asked like stupid questions that should never have been asked. And I don't feel that they really did that this time. There's a couple that I think were a little spotty. Um, Again, philosophically, I think are bad questions to be asking, but content-wise, they're fine. Okay. Remember, 70 questions, mostly randomized as far as the content goes. Okay. I would largely argue that they didn't randomize it fully, that it looks kind of like the first 35-ish questions are somewhat randomized first semester, and the last 35 are somewhat randomized second semester. Okay. So if you're aiming for 35, I would argue the first 35, in my logic may be flawed, are going to be an easier approach for you because that's older content that you've now constantly been practicing from last spring. Does that make sense? Whereas the newer content you've had less practice with and is now getting more specific to what chemicals are actually getting used. And I would argue that becomes a little bit more challenging to deal with because you just haven't practiced that content as much. Make sense? Okay. That's all I got to say on that. Just wanted to make sure you were aware of that. Next question. Go ahead. Oh, thank you for asking that because I've only asked it in email. Um, Officially, our scheduled exam time is Tuesday, next Tuesday, 11 to 12:50. I would argue you probably want a little bit more time to study, and I would push you to the Thursday. I didn't formalize that at the beginning of the semester, and because I did not formalize that at the beginning of the semester, both options are on the table. Okay. I would like to know if you're going to show up Tuesday or Thursday, because I'd prefer to not just sit in a room for 2 hours by myself. Um, Not that I haven't done that plenty of times before. Um, but yeah, does that make sense? So some people have emailed me with what they plan on doing. You don't have to necessarily email me, but just telling me is fine. But I'll be ready to go both Tuesday or Thursday. If nobody shows up Tuesday, I can spend all that time in the tutoring center, which does make sense for another segue. I should be in the tutoring center this Friday. I'll buy pizza this Friday, and I'll probably buy pizza one day next week, either Monday or Tuesday. Wednesday, I would start to argue, is getting close enough to exam time that you should be in just rote memorization at that point. So you aren't really asking questions anymore. It's just, I'm going to memorize all these facts. Does that kind of make sense? But Friday, Monday, Tuesday absolutely makes sense. I'll be there on Wednesday also for as much of the day as I can be. Um, but yeah, to encourage attendance, probably pizza Friday and then Monday or Tuesday. Sorry, I saw her hand first.
There's extended tutoring hours on Saturday till 4. It normally closes at 2, 7 till 4.
Okay, I will not be there on Saturday, but Saturday is open a little bit longer,
10 to 4?
10 to 4 on Saturday. Sounds like at least one of your colleagues is going to be there. So, and since they're there working, they would probably appreciate anybody from the class showing up because then they can officially study at the same time because they're quote unquote helping you. Sorry, Michael.
Yeah, when you're going to
I can try. The problem with me posting an announcement is that makes me feel like I really have to be there. And my schedule's a little bit wonky with chair rolls, and I've got to deliver some stuff over to Williams. But I'll try and get it posted, yeah.
We just want to know your moves.
Sorry, I'm making person.
Oh, yeah, what time was it on Thursday?
The exam Thursday, 11 to 12:50.
11 to 12.
11 to 12:50.
So same time as Tuesday.
Same time as Tuesday. And if you've got issues with that, feel free to send me an email. You do not have to announce it to the world that you have issues. You can send me an email. Yes.
What time are you going to be there on Friday?
All day.
All day. And
Nine, nine to 4. I have to leave at 4 to go get my kids.
okay. And how long is the tutoring center open on Friday?
How long is tutoring center open on Friday?
Till, no, it's like till 5 on Friday. I'm not there on Fridays usually, but I'm going Friday. But normally it's Monday through Thursday till 7, but Friday I think it's 7.
Friday's usually a little bit weird, but it's the Friday right before finals, so they usually expand the office hours. So I would bet 9 to 5, maybe 9 to 7. But yeah.
7 to 6. What neighborhood?
Well, that's where you would push for either Saturday or Monday, Tuesday, Wednesday. Because I certainly wouldn't be there that late.
I think it's 4 o'clock.
Is this the?
No, this is like
That's the one that is early dismissal.
I could be.
I think they have special finals hours.
Yeah, we do that.
Oh, and yeah, this says science tutoring is. That's at Williams campus. Never mind. Yeah, I think that they have special hours, and if they don't have special hours and they try to kick us out at 2, security can yell at me.
I'll ask them.
Security usually buckles when there's faculty there. But I could also just as easily move to a different room. Other questions? About logistics, studying, any of that? Okay, more smart work questions? It looked like everybody got through the basic EAS one, which was hopefully everybody that attended class. Everybody that did not attend class, I had no audio for, so the recording was kind of stupid, so I did not post it. Do we want to just go through smart work? Yes. Let's not go through science then. Let's go through 1 of 7. Even better, because she's not here. They're all grouped. Let's not just give it away to somebody who isn't here. I can't look at your questions. Cool. Here we go. Curved arrows, all they're trying to get you to go through and do here is just show resonance. And in particular, why would we care about this resonance? So the point of doing this resonance is kind of twofold. I would argue Cardi or whoever wrote this question kind of agrees with me philosophically in that you can look at the structures to determine where your chemical reaction is going to happen. Okay, remember, these are not what you're being asked for here are not sigma structures. Okay, because they're not sigma structures, these technically don't belong in a mechanism. So why are they, say that again?
This is sigma structure is positive.
Sigma structures are after you've done that electrophilic addition, okay, or electrophile addition, which means your benzene ring will have a positive charge on it. So in this particular case, what we're trying to do is get a feel for what atom X would do to the reaction. So atom X in this case would be that oxygen. And so what can happen is you can donate the electrons in. this shuttles electrons around, and if we look at that first structure, that's going to put negative charge on the ring. Negative charge on the ring makes it more nucleophilic. And if we go back to the simplified version of our EAS mechanism, the ring needs to act as a nucleophile. Kind of makes sense? Kind of feel like I'm getting dirty looks. I might be getting dirty looks because you're looking at that structure thinking that it was wrong. Okay, so let's fix that. Could just be getting dirty looks because it's me too. So if we draw out our structure, being able to draw resonance like this is going to be useful because you can absolutely get test questions saying, where would you put lone pairs? Which lone pairs are allowed to do resonance? So those kind of questions are fair game for the final. You won't be asked to draw the structures, but you'll be asked to interpret structures. So that first arrow dropped electrons in to make a pi bond. So that pi bond needs to be shown there. The next arrow shows the pi bond breaking, which means there's no pi bond there. The other pi bonds were left alone. Negative, our action started neutral and now has a positive. That's now the proper structure that belongs there. What happens next? You continue to do resonance. Again, doing the shortest possible hops possible. I know I said possible too many times. And if we go through and look at that, the next structure was drawn correctly. You would again go through that same process. Resonance, that was a little bit of a shaky arrow. Drawing out that final product, which was drawn incorrectly, so let's kind of erase that one for the moment and fix that drawing. Whoa, that was not what I meant to do. We aren't touching that oxygen, at least with the arrows that we've got shown, so all of that should be same. This double bond is the same. The lone pair moved in here to make that pi bond. Our other bond moved out, and that would then be our negative charge. Kind of makes sense? Yes, sir. So we are going to encounter a couple of things. If it's a bromine, is that what yours is? And they're asking for resonance? They're asking for resonance. They want you to show the lone pair donated, period. You're right. That's a little bit awkward because should it do resonance inwards? We'll know because you're forming multiple bonds to that bromine. Okay? But if they're showing you all the boxes there, it's probably just an algorithmic issue, and they should have picked a different species other than bromine. Okay? So why go through and do all of this? Okay, I would argue that statement is going to go to a different reason. Let's erase that. Because if we shift this to now kind of an ACS format, just pretend that none of that's there, what we could now get would be a question that says, where do we expect the negative charge to build? And you could get A, B, C, D. I don't know. We could run that as your 4 answer choices. Well, where do you expect negative charge to build? What answers would be valid? A, yes, and C. But if you're only focused on that one, you may stop after drawing one resonance structure. So you've got to propagate that resonance through the whole thing. Okay, for the record, ACS does not ask multiple select. There's only single select answers, which means we probably would have to drop D as an answer choice, and we'd have to switch this up into something more along the lines of A and B, A and C, B and C, or A, B, and C. Where's the negative charge build? Does that make sense? So you can see a string of possible answer choices on where you're building charge. So you need to pay attention to that whole structure. Ideally, when you look at that starting structure, you would recognize and be able to see that you would build negative charge at carbon A without having to draw. You would see that as you continue to do that resonance, you would build charge at C as well without having to draw. That takes a significant amount of brain power to hold that in there or hold that content. I would argue it probably makes sense to draw that out unless you are super confident at resonance. How many of you are super confident at resonance? So confident we want to share with everybody how confident we are. Okay? So if you're in a scenario that's being asked about resonance, you should draw it out. Does that make sense? Okay. You'll be given tons of scratch paper. Okay. You'll be given not clear paper. What did you say? You'll be given printer paper. There's the not transparency. What's the see-through-ish paper? Not carbon copy. Tracing paper. Fuck, I knew it was a T word. Okay, tracing paper. So you can put the paper on top because you're not allowed to draw on the exam booklet. Okay, you will lose significant points if you draw on the exam booklet. Do not do so. So you can put the tracing paper on top. You could draw your first set of curved arrows over the top of this drawing, draw that product, and now draw curved arrows on that next thing. Does that make sense? Instead of having to redraw everything from the very beginning. Okay? Your work will get collected. That work doesn't necessarily get graded, but if I see huge swings in expected scores, okay, for instance, I think you should score average and you're bombing the hell out of it, I'm going to double back to the work to be like, was there something in the work to cause me to believe you misbubbled somewhere so that I can get you those correct points? Okay? Believe it or not, that happens with all the other exams too, but I usually rely on you to help point that out for me. Since you can't point that out for the final, I have to go through and do that by hand. And it really only stands out for people on those kind of threshold lines. But I do go back and check that. Okay? So the more clear your work is with where you're writing things, the more likely I can feed you extra points if it is deemed necessary. Does that make sense? The follow-up question on this one, based on these resonance structures, okay, and this is the question that makes me think that whoever wrote this question is like me, not a true organic chemist, because a true organic chemist would never ask this question, because to decide where it's going to substitute, you would look at the resonance structures of your first step. You would have to look at the product. But when you look at those resonance structures, you would note that you're building charge at the A and C positions. And because you have it at the A and C positions, you're now trying to tie A and C back to ortho, meta, para. And so you could call attention to and bubble in this case, ortho and para. Kind of makes sense? Fun question. What if we change this up? And instead of doing BR2 and FEBR3, which are para-ortho directors, what if we instead did nitric acid and H2SO4, which are going to give us the NO2 plus, which is a meta director? Is this going to change your answer? And there becomes a critical aspect of this question. Okay? We're not talking about NO2 plus directing. We're talking about NO2 being added to the structure, doing the substitution. NO2 has no effect until it's on the structure. The structure that we've got still has an atom X that's para-ortho directing, which means my answer is still para-ortho directing. So don't get misleaded by the reagents causing you to shift answers. Does that make sense?
So the electrophiling, when it's not on the structure, it will never
Has
affect it.
no effect on the ring. It's only the substituents that are on the ring. What is atom X? Questions about that? Okay. I'm going to try and watch time a little carefully. Because there's a question that I'd like to make sure you're aware of. If it pops up. More curved arrows behind this. I care less about this overall question. So we'll go through it kind of fast. So this starts off right. Okay, our bromine donates electrons to that iron. The iron tribromide is acting as a Lewis acid catalyst. Why are catalysts cool? They So you started to get a little too specific for me. They increase the rate, yes, of the reaction, period. That's all a catalyst does. If it's a Lewis acid catalyst, it's now going to make the electrophile more electrophilic. Does that make sense? So be aware of where your catalyst is at, what's being asked if you're getting asked about catalysts. This is going to set up this goofy looking structure here. Okay, if we look, that big red thing is going to create the bond between the bromine and the iron, which is fantastic. We like that. Okay, we didn't touch the other sigma bond, so that should be left alone. And yet we're getting this question wrong. Why are we getting this question wrong? This was probably just an issue of lone pairs, okay, which is an extra frustrating one because of the sheer volume of lone pairs. Whoops, I drew too many on that one. So you would have to make sure that you've got your lone pairs drawn in for this. The charges look good all the way through, so that setup, that curved arrow is lovely. We don't want that positive bromine, so it's going to steal electrons from that bromine, which is now going to be our Br positive. Again, we're getting this marked as wrong. Why are we getting it marked as wrong? Exact same reason, lone pairs. Make sure you get your lone pairs in there. How many lone pairs should we draw on that bromine? Ooh, 3. Why only 3 pairs?
Oh wait, is it attached to the
It's positively charged.
6 individual?
Okay.
6 pairs.
Which is another fun question to be aware of, okay, which may or may not make sense next week. Okay, make sure you answer the question that's asked. If I ask for how many lone pairs there are, how many lone pairs are there? 3. If I ask how many electrons or unbonded electrons there are, 6. Okay, so changing the wording in the question can drastically change your output. Make sure you answer that question carefully. If we then continue through, we've got the lone pairs correctly done out there. We're talking about the pi bond reacting. Are all of those pi bonds equally fair to use to react with that positive bromine?
No,
Why not?
because you have a deactivating group. Am I getting specific?
Yeah, okay. Yeah, keep going.
Force the bromine into a meta position.
Okay. So which lone pair am I not allowed to use? Or sorry, not lone pair, bond.
We'll just say the 2 and the 4. The 2, 4, and 6 position. How about that?
Well, isn't that a 4 position? And that pi bond is now reacting?
Well, no. That's where the positive's going to be. I mean, if it's a pi bond, I share between 2.
Yes. So again, does it matter which pi bond I use? And you're still saying yes. And I completely agree with you, but you need a better explanation. Which pi bond, is there a pi bond I'm not allowed to use? Let's try that. Yes. The one adjacent to the nitrogen is the only one I can't use. Because if we look at the pi bond that was referenced here, it is shared between two carbons, but I can use that position, my 3 position, come on pen, my 3 position, which is exactly where it should go. It should go to the 3 position. Or I could have used the other pi bond over here. And again, I'd be talking about that position reacting. How do I know the circled positions are the ones that's reacting in this mechanism? True, but I have to add curved arrows. How do I know I'm saying that that 3 position, or if we'll label it out, that 5 position? Because I could use this curved arrow. So the blue one's not a question. The blue one can't react. How do I know the red one is talking about the 3 position reacting? How do I know the green one is talking about the 5 position reacting?
Because we're specified that one's going clockwise, so you'd have to use 3, right?
Wouldn't the 3 be going counterclockwise from where the pi bond is? So not a bad idea. I would argue the 3 position, if we look at the pi bond that's reacting, you'd be going counterclockwise. If we look at the green one, 5 position, you'd be going clockwise. So clockwise and counterclockwise don't work to explain this. It's kind of a gross answer. It's not that it doesn't matter. This mechanistic step gives me no information to tell me where it's going. Okay? Because that pi bond is shared between 2 carbons. I don't know where I'm trying to say that bromine goes until I specify where the bromine is at. How do I specify that? I have to move on to the next step. So it's only in this next step where I've shown where that bromine is located and ultimately where that positive charge is located that I now know where I've decided to place it. This is a problem with all electrophilic addition reactions, every single one of them, because you're reacting a pi bond, which has chemistry at both positions of that pi bond, both carbons of that. What is it, Schrodinger's cat? Is it Schrodinger's cat? Okay. Both those positions are equally active until you've defined which one reacted. We only know which one's reacted once we've drawn the product. Does that kind of make sense? I'm just going to agree with whatever that undo was about. Okay, so then they're asking for resonance. The resonance that they're talking about in this particular case is talking about what particular structures? Pen. That was an eraser. Those are all resonance structures of each other. Those carry a very particular name that you need to be aware of. Those are known as, these are sigma intermediates. Okay, so you're just dealing with resonance behind those. In the very last of those resonance structures, you'll note they're now continuing to carry the reaction on to our final product. So we would have to establish how that particular reaction worked. Okay, this is where this structure is going to come into play. Yes, the iron should have a negative charge. Does it have a lone pair? No, it does not. Okay, so we're going to fix that. We'd have to get rid of that lone pair. Okay, so why are we getting marked wrong? Shouldn't the negative attack the positive? How does this molecule react? as an acid. You mean it reacts with a negative attacking the positive hydrogen, not the oxygen. How is our iron tetrabromide reacting? What's the negative? Which is the basic atom. It's not the iron. Okay. So we got, whoa, that was a really big dot. Not at all what was intended to happen there. Number one, we need to make sure we've got our lone pairs in there so we could draw in our lone pairs all the way around, because this is super nitpicky about lone pairs. And then we'd have to talk about what's picking up that hydrogen. It's not the iron because it doesn't have electrons. What has the electrons are the bromines around the outside. So should we do the arrow from where the electrons are in the bromide? Why not? If we drew the result of that, we'd have the hydrogen connected to the bromine, which would then be connected out to your iron structure with all that junk. You'd have that positive bromine. We don't like that. Instead, where should we draw the electrons coming from? The bond between. Okay? That now separates that bromide from the iron tribromide structure. It reforms the iron tribromide, which was the catalyst that we started with. So our catalyst is reformed through the process of this reaction. And we form HBr. Okay? HBr is a strong acid. Some people, namely me, would complain about showing a mechanism that shows the formation of a strong acid in this particular reaction, and I would complain about that, yes. Would argue anything with electrons would pick up that hydrogen before the bromine. We may be in a system where that's all we've got. Kind of make sense? Oh, I totally ignored that. Good catch, thank you. If we go through and finish out the rest of those arrows aren't going to work. Okay? We need the electrons to stabilize, come on, pen, the positive on that carbon. If you take the electrons from here and put them there, you've got two hydrogens here. You would exceed the octet.
They forgot the bromine.
What do you mean they forgot the bromine?
One of the green hydrogens are supposed to be is a bromine.
So it's not green hydrogens. What should the bromide have attacked? Should it have attacked the hydrogen where the positive charge was? So
They forgot to draw bromine on the main structure.
Or the green hydrogens are. The two hydrogens, there's a bromine and a bromine.
oh, that's the mistake. Jiminy Christmas. Like, what are you guys talking about? There's no bromine. It's still that position that needs to react, but it's the hydrogen at that position, right? Come on, pen. We react with that hydrogen, which brings in the pi bond. Make sense? Good catch. At least we aren't in lab when you're exclaiming like that. This one is quite frankly gross. And we'll talk through why this one is gross. In my experience, we'll walk through what the common answer is, and then we can talk about potentially why it's not a good thing. So, what happens? That is NO2 plus. Okay, which means we need to do a substitution on that ring for our NO2 plus. Where would the most likely substitution spot be? What's going to dictate that? The identity of atom X. Does atom X have more electrons or less electrons than hydrogen? It has more. In fact, we have that lone pair, right? We're going to come back to that lone pair in a little bit. Okay, so what does that lone pair mean? With more electrons, we should direct to our para-ortho position. So drawing it in para makes a whole heck of a lot of sense. This is the most commonly accepted answer. Okay. And depending on the nuance associated with this, sometimes you get marked wrong, sometimes you get marked correct. It's a little bit frustrating in that respect. Okay. Why would this be wrong? Why is it being acidic matter? Yeah, that nitrogen is actually quite basic. And so typically, or a possible explanation for what can happen, is that you protonate that nitrogen. And if you protonate it, does atom X have more electrons or less electrons than hydrogen? It has less, which means it's a deactivator, which means meta-directing, which means your answer should be drawn with your NO2 at the meta position. Okay. Does that kind of make sense? This is a question that every time I see it pop up, I freak out about, regardless of where I've seen it. I've seen it both on the ACS and I've seen it in general test questions. I've seen it in lab exams, things like that. Okay. If we lean into this a little bit, okay, before we get to showing the answer, though, did the answer show it meta? Yeah. Okay. We have some people that are in the lab, right? Yeah? Is this the reaction you did in the lab? What did you do in the lab?
Bromine, right? Bromine, but that also had an acid, being an acid aspect to it, which
Yeah. So in lab, we went through and ran this reaction with whoa, God, I keep freaking doing that. That's my eraser. In lab, we ran through and did this reaction with Br2. That Br2 was made what's known as in situ. And in that in situ process, our Br2 came from hydrobromic acid. And what can you tell me about hydrobromic acid? It's a strong acid. And because it's a strong acid, what would you expect to happen? It should protonate the nitrogen. And if it protonates the nitrogen, what happens? It's deactivating group, which means the answer that we should get would be, just like SmartWork is trying to tell us is the result. Whoops. No, I did that right. We should put the bromine at the meta position. And those people in lab that analyzed the aniline starting material, what result did you get? And if we push on that a little bit, you didn't just get orthopara directing. What did you get? You got 3 substitutions, all orthos, all paras, saying that that nitrogen under those conditions was exceptionally activating, not even remotely deactivated. Okay, so this is a real challenging one to nuance and deal with. The, the bromide is being dealt with. And in an acidic environment would turn into H3O plus. So the dynamics behind this reaction are really, really nasty. Um, all I can tell you is that you should treat that nitrogen as an activator, regardless of the conditions. Is that true? Hell no. But for the sake of everything that you will see, treat it as an activator. Activator and para-ortho directing. After that, what do you have to trust? Maybe I should change the phrasing on that. Who do you have to trust? You have to trust that I pay attention to when that shows up, that you aren't getting tricked into a different answer. Sorry. Though at this point, you all have trusted me for at least 16 weeks. You can trust me for one more day, right? Or maybe you've learned to not trust me in that 16 weeks. But yeah, for this question, when you trust me, it's going to tell you you're wrong because they really wanted. Dude, come on. Fairly certain they wanted to see that meta substitution. Reset all the way back. Somebody had it open. Wendy, you had it open. Did they force you into the meta? Yeah. It wasn't you? Oh, yeah. They're expecting that meta, and not only are they expecting that meta, they're also expecting that positive charge on the nitrogen. Okay. Fun story. Also, they don't let you draw NO2, so you have to draw that out as the individual bonds. Don't forget the charges. Okay. Which, cool story. Typically, you will also see NO2 drawn as NO2. What's particularly irritating about drawing it as NO2? Doesn't show the charges, and in particular, it really doesn't show the charge on atom X. Atom X in this case is that nitrogen, and that charge is positive, which is why it's that deactivator meta director. Okay, so you do need to pay attention to that. Drawing out a full Lewis structure takes up valuable real estate. Most tests are not going to show it drawn out. Oh no, I know what's going on with this. What do we see? Two rings. Why is two rings potentially dangerous? Both those rings are potentially reactive. So before even pushing further into this, if you see two rings, both of them are potentially reactive, can you determine which one is more reactive than the other? Okay. This is where part of what you're being asked to do is to identify your atom X's on those rings. We've got that NO2. We just discussed that. That nitrogen is positive, which makes this ring deactivated. If we go through and look at well, actually, we'll push even further. Doesn't it also have an atom right there? Yeah. Does that atom have more or less electrons than hydrogen? Less. Why? The resonance of that carbonyl makes that partially positive, which means it has less electrons. That also means it's deactivated. Okay, so our leftmost ring is doubly deactivated. Oh, that's fun. What happens on our rightmost ring? False. Okay, let's go with that. Atom X. We've got the oxygen with the lone pair of electrons. That is a strong activator. I'll absolutely give you that. Now, what else are you saying? What? positive there. Are you telling me you could put a positive there?
Below at this H3C below that one. Isn't that a good area for a positive?
Yeah.
Okay. Isn't that making it?
Today is Tuesday.
Today is Tuesday.
Yeah.
Yeah.
So what do you mean? If I make that positive, what is that?
Well, when you're doing resonance, right?
Yes.
Mm-hmm.
Okay, I can do resonance. Give me more.
Tertiary carbocation is more stable than a secondary one.
Relevance.
Okay. So
Because I wants to jump in.
So I figured it out. It's an activator, but it's only going to react at the
What?
ortho position because we need a hydrogen. And there's no hydrogen on this ring.
Does atom X have more electrons than hydrogen? Yes, it is an activator. Which is, I think you were trying to go through this big long explanation of why it's an activator. I didn't need that. It has more electrons than hydrogen. Yes, it's an activator. But you're like, but you told her that she was wrong. She was wrong. She said there were two activators.
oh, there's more than two.
It's another atom X. So we have one ring that is doubly deactivated, and we have one ring that is triply activated. Okay, all the details matter. Okay, so if we're looking at triply activated, so we can, if we're going to run this chemical reaction, which ring would we expect to react? The deactivated one or the activated? The activated. Okay, so we're going to ignore the deactivated ring because that's not going to help us out. And so now we'll look at the activated ring. If it is activated, and we have three activators, where does my reaction happen? Well, if my yellow is my activator, where does it direct? Para and ortho. Can it react there? Nope. So I'm going to ignore that spot. It can't react there because I don't have the hydrogen. Remember, we're doing a hydrogen substitution. We could look at the ortho position. Again, that wasn't useful. So the yellow would direct here. Whoops, come on, pen. Would direct here. How about the red one? How about the blue one? Okay, which means where can we do the substitution? Anywhere on that ring. Okay, we do have a potential scenario where we have the most overlap. So if we're going to push blue, red, I guess we call that purple now, versus yellow, the blue, red make a whole lot more sense to run our substitution than the yellow. Everybody okay with that? We should actually be ignoring the red altogether. And this is one of the questions that I wanted to make sure that I got to when we talked about this today. When we're looking at multiple activators, the strongest activator dictates the overall reaction. So I don't care about the red or the yellow at all. I really only care about the blue. Does that make sense? That becomes an important kind of simplification is not the right word. Okay, but then that sets us up with two possible reactions. We could react at either of those two spots. Which one do you think is more likely to react? So closest. Is my hand closest, my right hand closest to my right pocket or my left pocket? My right pocket, really? Really? Okay. We have to be real careful with proximity because proximity can change. Okay. So our initial drawing may look like that's closest, but I could just as easily do a rotation of that sigma bond. Oh, I'm going to butcher the rotation pretty badly, I think. Trading about that. Actually, no. I totally lied. Because, yeah, what's that going to do? That's going to, and actually, nope, that's not right. So if I do that rotation about that bond, the OH is going to end up over here. Wrong marker. Stupid crayons. CH3 is there. These are my spots for my reactivity. Everybody see that? What does that become nice for us? Why does that become nice?
Isn't CH3 at the top position?
Yeah, it's in the other, right next to the.
Why is that nice for us?
It's not.
If we look at position 1 and 2, which one's going to react? Only position 1. Position 2, even if we do a rotation, isn't going to rotate into a spot that's going to allow an easy reaction.
Like steric.
Yep. So we get a steric prevention of position 2. How could we make this question harder? Because it wasn't hard enough. Instead of drawing it as we initially had drawn it, do the rotation. So position 1 and position 2 are far away from that chemical reaction. So you would have to do the bond rotation first, then run the chemical reaction. And you're like, but I don't want to have to do that. Tough. Tough. Okay. You are responsible for three-dimensional manipulations of your structures. Those, as you can see, I screwed it up. It can be very challenging to do those three-dimensional manipulations, particularly when put on the spot, standing in front of a classroom, or during an exam. Okay, so make sure you pay attention to those. Is it possible to do a rotation that would allow things to get closer to each other? That same rotation can be powerful for us because we could go through and we can rotate that part of my structure to be there. Why is that now extra beneficial? Make sure I didn't lose anything out here. Why is that useful? I can see the ring. What ring? That's the wording I wanted to hear. Whoops, we got a stupid eraser. Stop it. So on this one, our pi bond can come out and attack. The AlCl3 pulls the chlorine off, making our carbon extra positive. We can now close that ring structure. There's our benzene. OH, CH3. Pull that straight up. Pull that, whoops. Got a little bit excited about that one. Pull that one straight across to our carbonyl. And that gives us, as because I just suggested, a 5-membered ring. Oof, that's a 6-membered ring. We're just going to pretend. Kind of makes sense? So if you're seeing EAS stuff with 2 rings, make sure you identify which ring needs to react and then align where your chemistry should come together. We good? Yes. The 2 position isn't going to set up good sterics. I think I could draw a 3-dimensional product that would bring them pretty darn close. 1, 2, 3, 4, 5, 6, 7. Yeah, it would be a 7-membered ring though. If we did that rotation. Say it again? Just the formation of the ring. We're talking about sterics of our carbonyl reacting with carbon 1 or reacting with carbon 2. Carbon 1 is going to produce a 5-membered ring. Going to carbon 2 is theoretically possible, but it's going to form a 7-membered ring, which is sterically unfavored. You have to rotate this structure significantly around to actually get that ring structure to close.
If we were just adding chlorine, 2 would be better, right? Because
Okay. How do I clear? I don't think I can clear everything easily. So if we switch up the whole question now, okay, so there's a fun statement that I want to push on. It didn't say there was a ring formation, so I didn't know to look for that. Well, okay, that's also fair. Okay, when should you be looking for rings? Whenever they can happen, period. Okay, no question should ever tell you you're going to form a ring. Okay, all that's going to happen is it's just going to say run this chemical reaction. Is a ring a possible product? Does it form a stable structure? Yeah, then you form a ring. It has nothing to do with, oh, I got to do ring closing reactions. No. Is a ring possible? Yes, then do it. Done. There isn't an argument of, well, it didn't tell me to do that, because it will never tell you to do that. Okay? If we're going to look at this reaction and say, okay, we want to chlorinate now, there's a couple of things that should tip us off that we should be looking for that we didn't see. AlCl3 could be a reagent used to speed up a chlorine reaction, but we should see the Cl2 as a reagent. We didn't see Cl2 as a reagent, which means we shouldn't be doing a chlorination. If we decided, cool, we have Cl2, and we're going to do that, I'm going to have to delete that top piece because that top piece messes with it. I don't know why the chlorine up there didn't go away. Close enough. Ooh, now I got rid of it. If we're going to do a chlorination reaction, where should the chlorine go? Okay, it's going to have to go to our second ring. We talked about the ortho positions to our oxygen because our oxygens are driver on this chemical reaction. Which position is more likely to react? That top ortho position is sterically hindered. The bottom ortho position is not sterically hindered. We would predict the bottom ortho position to chemically react. Does that make sense? So entirely different question. Which, what's that? Aluminum chloride is a Lewis acid catalyst. It can be used in conjunction with chlorine or elemental chlorine, to make chlorine an active electrophile. So what's happening is you have that empty p orbital, pretend that's a p orbital. Okay, and what it can do is it can soak up the electrons of another chlorine, causing this bond to be super weak. Why didn't you specify that I had a chlorine on the other side? Because it doesn't have to be chlorine on the other side. What else could it be?
Carbon.
It could be the carbon of an acyl chloride. Okay, so the aluminum trichloride can show up in two places, chlorination or Friedel-Crafts acylation. Okay, with that, we are officially done, but for a couple reasons, mostly because I really have to go to the bathroom. Shouldn't have recorded that. Damn it. Oh, God. How do I stop the recording? Oh, now my foot's cramping. How do I stop it? Okay, I don't know how to stop it.